Hi, everybody. So today I'm going to finish up the material for the quiz and also big announcement for this Thursday, no lecture. The building where I'm giving this lecture is going to be having electrical work done. There's going to be no power. So this Thursday, quiz, but no lecture. If I think that we need a 45-minute makeup lecture, I'll just schedule one and tell you about it later. But this Thursday, we'll have the quiz as usual, but we won't have a lecture because we're not going to have any electricity in this building, and I have no place else to set up. Okay, so what we were doing last time and want to continue doing is going from a formula and a spectrum to a structure. So let's continue with that. Is the lab quiz next Monday? No, the lab quiz is next Tuesday. So please attend tomorrow's lab lecture for more information about that. Okay, so we're going from a formula and a spectrum to a structure. All right, so we have C7H14O2. And we're told that it's a ketone. All right, and the spectrum, let's draw the spectrum down here. The spectrum goes from 0 to 4 ppm. All of the peaks are between 0 and 4 ppm. Okay, and at about 1, we have a big, huge doublet. Big, huge doublet at 1. And this is worth 6 hydrogens. That's the integration that's telling you how many how many hydrogens are giving rise to that signal. At about 2 ppm, we have a big singlet. And that, I guess, is a 3 hydrogen singlet. And then a little bit shy of 3, we have a triplet. And that's a 2 hydrogen signal. And then close to 4, we have another triplet, which is another 2 hydrogen signal. And somewhere over here, we have a septet. 1, 2, 3, 4, 5, 6, 7. And this is a 1 hydrogen signal. And because it's hard to see, I'll just say it's a septet. Okay, so there's our spectrum. There's our formula. Let's figure out what is the structure of the molecule. All right, so now do I add up to 14 hydrogens? Hope so. 9, 10, 11, 12, 13, 14. Okay, first step is what? Calculate the DOUs. So how many DOUs in this formula? 7 times 2 is 14, plus 2 is 16. 16 minus 14 is 2. There is no halogen, there is no nitrogen. So the DOUs are 2. 1. 1 DOU because, 1 DOU. And we already know how that DOU is consumed because we're told it's a ketone, so we can immediately write our first fragment. All right, so we've taken care of the DOU, we've taken care of one of the oxygens. All right, so now my advice to you is to start with the most upfield signal or with the most downfield signal. They're the ones that are easiest to interpret. They're the ones that you're going to get the most mileage out of. So 6 hydrogens. What could possibly give a 6 hydrogen signal, this most upfield signal? 6 hydrogens. Is it a carbon atom bonded to 6 hydrogens? No. So tell me in the chat, what is it likely to be? Oh, it's likely to be 2 methyl groups. Is that the only thing it can be? No, it could be 3 equivalent CH2s. It could also be 6 equivalent CHs, but we'll go with the simpler alternative, which is 2 methyl groups. It's split into a doublet. So what does that mean about who lives next door? Tell me in the chat, how many hydrogens live on the carbon next door? It's just going to be 1, right? Because we have this signal is split into a doublet. So there's just 1 hydrogen on the neighboring carbon. Now, if this is not just to be a fantasy, the spectrum better have a 1 hydrogen signal somewhere in it. Oh, it does, right here. It's a septet, right? And so the septet is telling you how many carbons live next door to this guy. This is a septet. How many carbons live next door to this guy? It's going to be 6, right? Because that's why it's split into a septet. And do I have a 6 hydrogen signal somewhere in the spectrum? Here it is. So everything matches up. We can draw our first fragment. So we have 2 methyl groups, and they're equivalent to each other. Whatever I do to one of the methyl groups, I have to do to the other methyl group, or else I will lose their equivalence, and it's not going to be a 6 hydrogen signal anymore. Okay, this 1 hydrogen septet here, he split into a septet by these 2 methyl groups. So how many hydrogens live on the carbon over here? None, right? Because we would have more splitting than a septet if there were any hydrogens on the carbon that lives up here. But now when we look at the chemical shift here, we see it's close to 4. So what is that telling you about who lives here? It can't be a carbon with any hydrogens on it because we'd have more than a septet in the splitting. So who has to live here, right? The chemical shift, the splitting, the integration, they all work together, right? So who we have here is an oxygen. That's why that chemical shift of that height of this proton is so far downfield, around 4 ppm. Oxygen forms 2 bonds, so we better give that fragment oxygen another bond to remember to link it up. Okay, so now let's go downfield, right? My suggestion to you is you start with the most upfield signal or with the most downfield signal. Let's go downfield. So this guy over here, he's a 2 hydrogen signal. What fragment does that suggest? 2 hydrogen signal. That's going to be a what? It's going to be a CH2. Is that the only thing it could be? No, it could be 2 equivalent CHs. Let's go with the simpler alternative. And what is the chemical shift telling you about this CH2? Why is it so far near 4 ppm? Why is it near 4 ppm? Oh, it's next to the oxygen, sure. So that guy lives here, right? And now what is the, let's see, I better label all these things. I'm going to call this guy A, right? That was A, and this was A. I'm going to call him B. I'm going to call him C. I'm going to call him D. So that was D. I'm going to call him E. So I just found a home for E. He's here. And now what is the triplet splitting of this downfield triplet telling you? How many carbons live next door? We're looking at E, right? It's split into a triplet. How many hydrogens live on the carbon next door? Yep, another CH2. Is there another CH2 somewhere in the molecule, in the spectrum? Yeah, here it is right here, right? So these must be the C protons. And carbon forms 4 bonds, so we better give that carbon an extra bond. Okay, we've taken care of E, we've taken care of D, we've taken care of C, we've taken care of A. Let's take stock. What are we looking at? What are we still missing? We need 7 carbons. 1, 2, 3, 4, 5, 6 carbons showing. We've taken care of our degrees of unsaturation. We've taken care of 2 oxygens. We're so close. We're almost done with this problem. Okay, a 3 hydrogen signal. So what fragment does that imply? A CH3. And then when I look at my table of chemical shifts, I see that a hydrogen bonded to a carbon, which is bonded to a carbonyl carbon, that's at about 2.1. So this CH3 group, that must live here, right? I'm getting its location from the chemical shift. And so there are all of my pieces of the puzzle. So that's the that's the structure of this molecule. Okay, so written out in a, so this would be the B proton. So written out in a prettier way, maybe looking something like this. So how'd that go? Yes? Anything for me in the chat about problems like this? We have time to do one more and then we have to move on to something else. Okay, so speak now or forever hold your peace. Okay, so let's do this one. C7H14O2, and we're told it has no carbon-oxygen double bond, so it's not a carboxylic acid, it's not an ester, it's not a ketone, so it has no carbon-oxygen double bond. And the spectrum from 0 to 6, 0, 1, 2, 3, 4, 5, and 6. Well, I should have made that bigger because you get all squunched up. Okay, near 5 ppm, near 5 ppm. Forgot to turn on my mic. So much stuff I have to do here. So much stuff to remember. All right. Okay, so at around in the 5s, I have a triplet worth 1 hydrogen. And then a little bit past 4, I have a doublet that is worth 2 hydrogens. And then right close by, I have a big 3 hydrogen singlet. 3 hydrogen singlet, and then a little bit closer to 3, I have a quartet, which is worth 2 hydrogens. And then near 2, I have a triplet, 3 hydrogen, 3 hydrogen, triplet, 3 hydrogen singlet. And then my most upfield signal is a 3 hydrogen triplet. Okay, so there's the spectrum. So let's figure out the structure. So how many DOUs? C7H14O2. Oh, it's exactly like the problem we just did, right? So this is a DOU. It's the very same formula. It must be a constitutional isomer. So it's the same formula, same degrees of unsaturation, 1 DOU. So let's start with the most upfield signal. Right? Remember this upfield signal, this is going to be farthest away from a multiple bond. It's going to be farthest away from an electronegative atom. It's a 3 hydrogen triplet. So what fragment does that suggest? CH3, correct? And now it's a triplet. So who lives next door? It has to be a CH2. So I'm calling this guy A, I'm calling this B, C, D, E, and F. Okay, so this 3 hydrogen triplet, that's A. He split into a triplet, so that means there's two hydrogens next door. Is there a two hydrogen signal somewhere in the spectrum? There is. There are two of them. But notice one of them is a doublet and one of them is a quartet. So this guy can't belong, this guy can't be E because he wouldn't be split into a doublet. He would have more splitting. So this guy here has to be C. It's this two hydrogen quartet split by these three methyl groups. And what is the chemical shift telling you about this two hydrogen signal? What's the chemical shift that are in the threes telling you about who lives here? Anybody? Who lives here? We're looking at C. Why is the signal at around 3? Well, that has to be an oxygen, and oxygen forms two bonds, right? So we've taken care of A, we've taken care of C. So we have that fragment. Okay, and so now let's look at the most a downfield signal. This is a one hydrogen, it's a one hydrogen triplet. Okay, and look how far downfield it is. Right, so what is the chemical shift telling you about this guy is that it's probably close to this electronegative oxygen, right? But it's even further downfield than where we would expect it to be if it were just close to one oxygen. So it's either close to a second oxygen, or the other alternative is that it is close to a multiple bond. Right? We have a DOU of 1. That means, and we have no carbonyl. So that means this degree of unsaturation is either going to be a ring or a multiple bond. And I'm looking at the downfield shifts of some of this guy, and this is squarely in the alkene region of the NMR. Where am I getting that? From my table of chemical shifts. So F, so this guy here is probably an alkene proton, right? It's too far downfield just to experience the electronegativity effect of one oxygen. So it's either close to the second oxygen or it's an alkene proton. Okay, let's table that for a second. All right, so here I have a 3 hydrogen signal over here. So that's a methyl group. And what is the downfield chemical shift of this 3 hydrogen signal telling you? Who lives here? It's probably the second oxygen, right? It's in the 3s, and that's where we expect a signal from a proton that is 2 bonds away from oxygen. Okay, so that's D. Okay, so we're doing pretty good so far. All right, so now what else do we have? We decided that this guy here, he's in the alkene region of the spectrum between about 5 and 7 ppm. So this is a 1. So here we have a carbon-carbon double bond. Here we have a carbon-carbon double bond. And I'm going to put F on this carbon-carbon double bond system, but he's a triplet. Right? So he has to be split by a CH2 group. So this guy here, I'm going to put him here, and I'm going to put a CH2 here to split him into a triplet. So that's F. And I knew this was an alkene proton because his chemical shift in the 5s, that is typical of an alkene proton. Okay, so how am I doing? I'm looking for 7 carbons, 1, 2, 3, 4, 5, 6. I'm just looking for one more carbon. And I've explained, I found a home for A, for C, and for F. Okay, so now what? Who's left? Oh, B. This is going to be easy over here. So that's a 3 hydrogen singlet. So that means a CH3. right? And there are no hydrogens on the carbon that lives next door. Otherwise, he wouldn't be split into a singlet. So how am I doing? 1, 2, 3, 4, 5, 6, 7. I'm looking at all my carbon. I'm looking at all of my degrees of unsaturation. I'm looking at all of my oxygen. All that I have to do now is hook the fragments up. Okay, so I'm probably going to put this guy here. Why? Because this methyl group is close to a double bond. Remember, electronegativity is not the only thing that determines the chemical shift. It's also how close is something to a multiple bond. So that this methyl group is probably bonded to this methyl group here. And now I could either put this guy here or I could put this guy there. Both seem reasonable. So what I'm going to do is I'm just going to hook this guy up here, and I'm going to hook this guy here. Could I have hooked up the other way? Probably yes. But I'm thinking that's a very reasonable deduction of the structure. So written out in a pretty way, I would get that. Okay, so there's my spectrum. There's my structure. Okay, so now I want to go on to something, finish up the material for the quiz, and I'm going to talk about what we call complex splitting, as if simple splitting weren't complex enough. On top of that, we have something that is complex splitting. Okay, when to look for complex splitting? All right, so we know when to look for simple splitting, right? Let's just review that. When the observed proton is 2 or 3 bonds away from n other protons, and the observed proton is not equivalent to those n other protons, but those n other protons are all equivalent to each other, then we're going to have simple splitting, or n+1 splitting. Okay, in complex splitting, what we're going to look for is the observed proton is 2 or 3 bonds away from n other protons that are not equivalent to H observed. And, okay, so here's the difference, right? And the n other protons are not equivalent to each other. That's when we're going to get complex splitting, right? We get n+1 splitting when the proton is, the observed proton is 2 or 3 bonds away from n other protons, but those n other protons are all equivalent to each other. What happens when they're not all equivalent to each other? That's when we need complex splitting. So let's look at an example here. Maybe something like this. We would have an ester, and maybe CH3 here. All right, and make this guy the observed proton, right? And so here we see, here's an example where we're going to need complex splitting. The H observed is split by the HA. The H observed is also split by the HB, but the HA are not equivalent to the HB. So that's when we need complex splitting. So these guys here, for them right here, we need complex splitting. Why? Because the HA are not equivalent to the HB, and the H observed is split into, is split by two sets of protons that aren't equivalent to each other. Okay, so that's the situation that you're looking for complex splitting. Okay, handling complex splitting is very complex, right? Is that we have some situations where the complex splitting can be readily understood. We have other situations where the complex splitting, you need to have a computer program to analyze the splitting, right? We're not going to get into that right now. We're going to get into just the situations, favorable cases, easy cases of complex splitting. Okay, in favorable cases, the complex splitting is analyzed, it's understood as a sequential application of N+1 simple splitting. All right, so this isn't always going to happen. Like I said before, sometimes you need to have a computer program to understand the splitting. But in some other cases, we don't. So what do I mean by the sequential application of N+1 simple splitting? So if we go back, if we go back to this molecule that we had before, that we just finished talking about, the H observed, and this guy here. So let me remind you about this. If you're lucky, the HA, if you're lucky, the HA splits H observed into a what? Forget about HB for now. Just look at HA. The H observed is going to be split by HA into a what? Anybody out there? The H observed is split by the HA into a triplet. And the HB splits the H observed into a what? The HB splits the H observed into a what? Into a quartet. So in favorable cases, the signal of H observed is either a triplet of quartets, or, right, in other words, I turned on the triplet splitting, then I turned on the quartet splitting. I'm going to get a triplet of quartets or a quartet of triplets, right? And a triplet of quartets, that's abbreviated TQ. A quartet of triplets is abbreviated QT. And which it is, we're going to talk about that. So hold on. All right, so this is what I mean by sequential application of N+1 splitting, is that I turned on the splitting to HA. Then I turned on the splitting to HB. I got a triplet of quartets, or I could have done it in the reverse fashion. Turn on the splitting to HB, I get a quartet, and then turn on the splitting to HA, I get a triplet. So this is what I mean by sequential application. The most common complex splitting multiplet is called the doublet of doublets. This is the most common, favorable, right? One in which you can do this sequential application of n+1 splitting. Most common favorable complex splitting is the doublet of doublets. This is abbreviated DD. So that means I have a proton and it is split by one proton on this side and one into a doublet, and then one proton on this side into another doublet, but those two protons that are splitting the observed proton are not equivalent to each other. That's what's going to give me the doublet of doublets. I turn the splitting onto the left, I get a doublet. Then I turn the splitting onto the right, I get a doublet. So that's where the doublet of doublets comes from. Okay, and so now let's look at a situation where we would see something like that, like this. For example, in this molecule, okay, so in this molecule here, the H observed is split by the HB and by the HA, but the HA and the HB are not equivalent to each other. So that's where I need simple complex splitting. I need complex splitting. I turn on the splitting to A, and then I turn on the splitting to B. And what the NMR pattern looks like, it's called the doublet of doublets. What the NMR pattern looks like depends on the coupling constants, right? The appearance of the signal of H observed depends on the coupling constants, which are abbreviated J. Okay, so we talked about coupling constants, and remember the coupling constants. That coupling constant, that's the distance between peaks in the multiplet, right? That's what J is, the distance between the peaks. Okay, so you don't have to memorize any coupling constants for the quizzes and for the final exam or whatever. I'll give you a table of coupling constants. If you look at the study guide for this week's quiz, I have a table there. You can also look them up online. I wouldn't necessarily suggest that, but you could. Okay, so let's see what this doublet of doublets looks like. Okay, so I'm looking at my table of coupling constants, and I see that an alkene proton split by a proton 2 bonds away, right? 2 bonds away, and where that splitting proton is on the same alkene carbon, this coupling constant here, I'm going to call that J-gem, meaning geminal, meaning the observed proton and the splitting proton are on the same carbon. This guy is worth about 2 hertz. Okay, so I'm just getting that from my table. That's just data. Okay, I'm looking at that table of coupling constants, and I see that the an alkene proton that is 3 bonds away from another alkene proton, and where the splitting alkene proton is cis to the observed proton, that coupling constant is about 10 hertz. So I'm calling this J cis, and it's equal to 10 hertz. Okay, so that's all of the information I need to be able to visualize what the splitting pattern of this doublet of doublets is going to look like. And what we use to determine those splitting patterns, this is called the splitting tree. Okay, so let's go through how to make a splitting tree. Here's the observed proton, right? Unsplit signal. We haven't turned on any of the splitting yet, right? It's just a singlet. And now we're going to turn on the splitting. Now, it doesn't matter whether you turn on the J cis or the J gem first. It doesn't matter one bit. But you get a much prettier picture, a much easier to understand splitting tree if you go from the widest splitting to the narrowest splitting, right? But it doesn't really matter which coupling constant you turn on first. I'm going to turn on the J cis, and that's going to be a 10 hertz coupling constant. Okay, and so this is split into a doublet, and the peaks of the doublet are separated by 10 hertz. I'll do this later on a piece of graph paper. I'm just going to do it freehand now because I don't really need graph paper for this simple problem. So I take this unsplit signal and now turn on the doublet splitting. Turn on the doublet splitting of J cis, right? And this distance here, imagine I'm doing this on a piece of graph paper, that's 10 hertz. Okay, so I turned on the J cis coupling. All right, now, right, we're talking about complex splitting. We're talking about how if we're lucky, complex splitting is a sequential application of simple splitting. We've just turned on one of the splitting patterns. Now we're going to turn on the other splitting pattern, the J gem. And that is going to be another doublet where the peaks are separated by 2 hertz. Okay, so this guy here, he split into a doublet of his own. And the peaks in this new doublet are 2 hertz away from each other. So that was 10. 2 is going to be a lot narrower. See how I split it into a doublet? And that is worth 2 hertz. Now I'm going to do the same to this other doublet over here. He split into a little doublet of his own, but because of the J gem splitting. So he split into a little doublet of his own where the peaks are separated by the coupling constant of 2 hertz. There I've turned on J gem. All right, so you get it, right? This is what I mean by sequential application, and what the multiplet is going to look like is going to be this doublet of doublets. All right, I'm ready to sketch the pattern of H observed. All right, so I'm through with all of the splitting. So the pattern is going to look like this. It's going to have a peak there. A doublet is 1 to 1, right, by Pascal's triangle. So these 2 peaks are exactly the same height or very close to the same height. I'm going to have another peak there, and then I'm going to have a big empty space here. And then I'm going to have another peak here, and then I'm going to have another peak here, and that's what my doublet of doublets looks like, right? That's my DD. Why is it called a doublet of doublets? Because of this. Look, there's the unsplit signal. I'm going to split him into a doublet. And then I'm going to split him into a doublet. Then I'm going to split him into a doublet. It's a doublet of doublets. If I were to take this and go across the street and you would look at it, you'd say, well, I see some peaks there. I see some peaks there. I'm too far away. I can't really tell what they are, but it kind of looks like a doublet. It's a doublet of doublets, right? But the shape of the doublet of doublets depends entirely on the coupling constants, right? So there's my unsplit signal. There's my first doublet. There's this guy split into a doublet. This guy split into a doublet. But what the doublet of doublets looks like depends on this splitting, and it depends on this splitting. So these lines can be close or far depending on what the coupling constants were. That's why we need this splitting tree. All right, another thing to notice that it's four components, right? But it's not a quartet, because a quartet is 1 to 3 to 3 to 1 by Pascal's triangle. This is not 1 to 3 to 3 to 1, right? This is 1 to 1 to 1 to 1. It looks like 4 lines of more or less equal height, right? And so this is how we can tell that we see 4 signals, but it's not a quartet. It is a doublet of doublets. Okay, so let's try this doublet of doublets splitting tree again. But now let's look at another situation. Let's say here we have the observed proton. All right, and he is bonded to a carbon, and then 2 bonds away, I'm going to put HB, and then 2 bonds away, I'm going to put HA. And now, let's see, I'm just going to make up a molecule here. And I want to make HA and HB not equivalent to each other. So I want to take care of that. So maybe I'll put a Cl there and a Br there. Maybe I'll put a methoxy group here. And now I want HA to be different from HB. So maybe over here, I'll put a methoxy group over here and maybe put a Cl there, right? Just a crazy molecule that I just made up to make HA and HB different from each other. Okay, the observed proton will be split by the HA and the observed proton will be split by the HB. But what I'm trying to tell you is that what the doublet of doublets looks like depends on the coupling constants, right? And I have to be told what the coupling constants are, or if I have a very good feeling for NMR, I can make a really good guess of what the coupling constants are. Let's say in this case, JA is equal to 6 Hertz. That's the coupling constant due to A. And now let's also say that JB is also equal to 6 Hertz, right? So here the 2 coupling constants are accidentally equivalent to each other, right? What will the splitting tree look like now? Right? In the previous example where the coupling constants were different, very different from each other, I got this doublet of doublets pattern. Here I'm making the 2 coupling constants equal. Will the splitting tree look exactly the same? All right, so let's go through how to draw a splitting tree. Here's the observed proton, unsplit. It's a singlet. Now I'm going to turn on the splitting to A. And then I'm going to turn on the splitting to B, or I could have done it in the reverse direction. It doesn't matter. So it's just sequential application of N+1 splitting. All right, so let's turn on the splitting to HA. We get a 6 Hertz doublet. So something like that. This is 6 hertz. Right? I've turned on the splitting to HA. Okay, now I'm going to turn on the splitting to HB, where each of these doublets is now split into a doublet of its own. So this guy is split into another 6 hertz doublet. I turned on the JB splitting. So this guy is split into a doublet of its own. So that means I go out 3 in this direction. I go out 3 in this direction. Boom. I go out 3 in this direction. Boom. Right? This is 6 hertz. Okay, now I'm going to split this other signal into a little doublet of his own as well. So with this 6 hertz coupling. So I'm going to go out 3 hertz in this direction. Oh, these lines pile up. I get this position twice. See how I made it twice as long? Because now the lines have piled up on top of each other. And then I go out 3 hertz in this direction. Boom. So here's 6 hertz. What is the pattern going to look like? I'm going to get a signal there, 1, that's going to be worth 1 unit in height. I'm going to get another signal there, which is going to be worth 2 units in height. I'm going to get another signal here, which is going to be worth 1 unit in height. I got a triplet. I got a 1 to 2 to 1 intensity ratio. I got a triplet. So the important thing to notice here is that when the coupling constants, when all the J's are equal, the complex splitting pattern simplifies to a simple splitting pattern. When all J's are equal, the complex splitting simplifies to simple n+1 splitting. Right, so you know what? I have a little attendance indicator here on my Zoom. And although there are 70 people registered for this course, I see that only 35 people have tuned in. So let's say you never heard about complex splitting, right? You're in the 50% of the class that isn't tuned in right now. Let's say you never heard of complex splitting. And you were saying, well, H observed is 3 bonds away from HA. It's 3 bonds away from HB. So H observed has 2 neighbors. N equals 2. 2 plus 1 is 3. The splitting pattern of H observed will be a triplet. You'd be right in this case, because all of the coupling constants are equal, right? So you never heard of complex splitting. You only heard of n+1 splitting. You think that n is just the number of neighbors. Here, H observed has 2 neighbors that can split it. N equals 2. 2 plus 1 is 3. You get a triplet. And you do, but that is only because the coupling constants are all equal to each other. When they are not equal to each other, you're not going to get a triplet. You're going to get this doublet of doublets. So this guy is a doublet of doublets, comma, right? But it looks like a triplet because just accidentally all of the coupling constants are equal. Okay, I'm going to take my break now of about 10 minutes, And then my clock says 9:50. I'll be back in 10 minutes. And then I'll continue and conclude talking about the complex splitting. Okay, hi everybody. Once again, I'm back from my break. So I want to show you some NMR spectra that show the doublet of doublets and some other complex splitting multiplets. So in this molecule here, we see the most downfield signal that is split into 4 components, right? This is split into 4 components, but it's not a quartet, because a quartet would be a 1 to 3 to 3 to 1 pattern. This is a doublet of doublets, 4 components of approximately equal height. Okay, so that's what a doublet of doublets looks like. And you know, these signals over here, believe it or not, they're also doublets of doublets. But this is a very nice isolated doublet of doublets. So you can see the approximately 1 to 1 to 1 to 1 pattern over here. Okay, we talked about how the appearance of the multiplet depends on what the coupling constants are, and that's why we like to use that splitting tree. Okay, so this slide here shows the H observed is split into a doublet by the HA, and it's split into a triplet by the HB. But the HA and the HB are not equivalent to each other, so that's where we need this complex splitting, the sequential application of simple splitting. But what the pattern looks like is going to depend on the size of the coupling constants. Okay, so over here on the extreme left, this is called a triplet of doublets. See, if you squint, this looks like a triplet. But if you zoom in, let me see if I can zoom in. If we zoom in, on that thing that looked like a triplet, if we zoom in on what the thing that looked like a triplet, we see it's not, is that this thing, which kind of looks like a triplet if you squint, it's each of the peaks in the triplet is actually a tiny little doublet of its own. So that's why this is called a triplet of doublets. It is doublets arranged in a triplet pattern. On the other side of this slide, you have the doublet of triplets, right? So this pattern, if you squint, it kind of looks like a doublet. But when you zoom in, you see that each peak in that doublet is actually split into a tiny little triplet of its own. So that is why this is called a doublet of triplets. It is triplets arranged in a doublet pattern. And the reason that these signals look different is because the coupling constants are different. Here, the JA is, the JA here, the triplet splitting is much smaller than the JB. Here, the JA is much bigger than the JB, right? Now, right here in the middle is something I called a Q, a quartet. Because again, like I said, if you never heard of complex splitting, you would say, well, the observed proton is split by 3 other protons. N equals 3. 3 plus 1 is 4. That's going to be a quartet. And it is, or it looks like a quartet. It looks like a quartet because all of the coupling constants were equal just by accident, and it's going to look like a quartet. But when some of these other when the coupling constants aren't either very different or equal to each other, then you're going to get some very weird looking patterns here, right? Here I see 1, 2, 3, 4, 5, 6 components in this TD over here, but it's not a sextet, right? Because it does not follow the Pascal's triangle sextet ratio. Over here, I have 5 signals, 1, 2, 3, 4, 5 signals, but that's not a quintet because the intensity ratios do not follow the quintet pattern. Okay, so now let's look at some more doublets of doublets. So if we look at this molecule here, we see the HA is split by the HB and the HC, but the HB and the HC are not equivalent to each other. The HB is cis to a bromine, the HC isn't. So HB and HC are not equivalent protons. They're going to split HA into a doublet of doublets. And see what the doublet of doublets looks like? Well, I see 3 signals. I see 3 components, but it's not a triplet because a triplet is 1 to 2 to 1. And this is nowhere near even being 1 to 2 to 1. Okay, so HC is also split into a doublet of doublets by the HA and the HB. And if we look at the signal of HC, well, that looks like a triplet, right? It's actually a doublet of doublets where all of the coupling constants were about the same. So this looks like that 1 to 2 to 1 intensity pattern of a triplet. It's not a triplet, it's a doublet of doublets where all of the coupling constants were accidentally the same. HB is also split into a triplet by HA and HC. And again, the coupling constants here were not equivalent. I get 3 components, but it's not a triplet. It's a doublet of doublets. A triplet would have a 1 to 2 to 1 intensity pattern. Okay. So how about let's practice drawing some splitting trees, shall we? This is the observed proton. What would be the splitting pattern of the observed proton, right? We don't know exactly what it is until we're given the coupling constants, but let's just take a guess. Anybody? What would be the splitting pattern of the observed proton? Anybody want to give it a shot? Doublet, oh, a little bit more than that. Triplet. I thought we were talking about complex splitting. Let's try again. Well, doublet of doublets, well, at least now we're remembering we're talking about complex splitting, but it's not a doublet of doublets. Let's try again. How about a doublet of triplets or a triplet of doublets? Right. Because the observed proton is 1, 2, 3 bonds away from HA, 3 bonds away from 2 HAs, and 3 bonds away from an HB. But the HAs and the HBs are not equivalent to each other. So that's where we're looking for complex splitting. Okay, so H observed is either going to be a doublet of triplets or a triplet of doublets or something, or something in between. If all the coupling constants are equal, what would it be? If all the coupling constants were equal, what would the splitting pattern of H observed be? It would be a quartet, right? Okay, but it's not going to be a quartet because it turns out in this molecule, this guy here I'm going to call that JB is equal to 10 hertz, and JA is equal to 6 hertz, right? So it's not going to be a quartet. It's going to be one of those other patterns. Okay, so let's see. At the risk of this being a total flop, I got some graph paper. So I'm going to try to do this on some graph paper. So I'll just make a synopsis over here. What's the molecule we're looking at? Molecule we're looking at is this. And this is the observed proton there. And these are the HA, these are the HA, and here's the HB, right? And JA is what I say, 6 hertz. JB is what I say, 10 hertz. Okay, so let's draw what the splitting pattern is going to look like. So I'm going to start, there's my unsplit signal. There's my unsplit signal, and I get a prettier picture if I turn on the wider coupling, the widest coupling first. So I'm going to turn on that I'm going to turn on the splitting to the JB, and that's going to be a 10 hertz coupling, right? And remember, the J is the distance between the peak. So I need to split this guy into a doublet. I'm going to go 5 to the left. Hope it's all going to fit on this paper. I'm going to go 5 to the left. 1, 2, 3, 4, 5. Boom. And now I'm going to go 5 to the right. 1, 2, 3, 4, 5. Okay, so there's my J. This is my JB of 10 hertz. And now each of these is now going to be split into a triplet. And the distance between the peaks in the triplet is going to be 6 hertz, right? So it's a triplet, and the triplet, it's three components. The middle component is centered right underneath this line. So this guy, I'm going to make him, right? And remember, the triplet has a 1 to 2 to 1 intensity pattern. Excuse me. I conveniently made this line 4 squares long. So now I'm going to split this guy into a triplet with a 1 to 2 to 1 intensity pattern. So that means 2 squares high there. And now go out 6. Go out 6. 1, 2, 3, 4, 5, 6. Oh, thank God, it fit on the paper. 1, 2, 3, 4, 5, 6. And now go 6 out in the other direction. 1, 2, 3, 4, 5, 6. And make that. So there's my doublet splitting, and here's my triplet splitting. And you see how it's 1 to 2 to 1. Okay, now I'm going to do the very same thing with the other guy. I'm going to do the very same thing with the other guy and split him into a 6 hertz triplet with a 1 to 2 to 1 intensity pattern. So the middle line of the triplet is going to be right underneath the previous line, and now I'm going to go out 6 to the left. 1, 2, 3, 4, 5, 6. Now I'm going to go out 6 to the right. 1, 2, 3, 4, 5, 6. And so here's my splitting from the JA. Okay, so I've applied all the splitting. What is the pattern going to look like? It's going to be a peak 1 unit high there, and then it's going to be a peak 2 units high there, and then it's going to be a peak 1 unit high there, and then another peak 1 unit high there, and then another peak 2 units high there, and then another peak 1 unit high over there. So what do you think we would call this? Would we call this a doublet of triplets or a triplet of doublets? What does it look like to you, if anything? Is it a doublet of doublets, or is it a doublet of triplets or a triplet of doublets? Oh, it's a doublet of triplets. That's what we would call it. A doublet of triplets. Is it a doublet of triplets? It's not a triplet of doublets, because a doublet is 2 equally spaced lines. A triplet of doublets, it would look like a triplet, but each of those peaks in the triplet would be split into a little doublet of its own. So we would call this a doublet of triplets, but we only know that once we are given the coupling constants. So how did that go? Yes? All right. Let's do a structure determination problem that involves complex split. C6H10O2, C6H10O2, and we're told it's an ester. All right, and the NMR whoa, the biggie. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so down here in the 7s, I have something that looks like this. 1, 2, 3, 4. See how it's 4 components? But you see how it's not a quartet? That's a doublet of doublets, and it's worth 1 hydrogen. Okay, and then at around 5 ppm, I have something that looks like a doublet. And then over here in the 4s, I have something else that looks like a doublet. And this is worth 1 hydrogen. This is worth 1 hydrogen. But now when I zoom in, what I see is that this guy is actually a doublet of doublets like this. And the upfield guy is also a doublet of doublets, right? But I didn't know that until I zoomed in. Right, so that's a doublet of doublets, and that's a doublet of doublets as well. Okay, and then a little bit past 3, I have a triplet, which is worth 2 hydrogens. And then a little in the 2s somewhere, I have a sextet. 1, 2, 3, 4, 5, 6, which is worth 2 hydrogens, and that's a sextet. And then at about 1 ppm, I have a big triplet. Which is worth 3 hydrogens. Okay, so there's the spectrum. What's the structure? How many DOUs? 6 times 2 is 12, plus 2 is 14. minus 10 is 4. There is no halogen. There is no nitrogen. So this is a DOU equal to 2. And I'm told it's an ester, so I know how one of the DOUs is eaten up. One of the DOUs is eaten up by a carbon-oxygen double bond, so I can write my first fragment over here. So I've just taken care of all of my oxygen. I've taken care of one of the 2 DOUs. Okay, so now let's talk about this sextet. So how many, it's a sextet, how many neighbors does this, do these protons have? How many neighbors to give it a sextet? How many neighbors? Oh, it has to be 5. Okay, but let's think about that for a second. Does that mean that these protons are next to a carbon that has 5 protons on it? No, because carbon only forms 4 bonds. So what could a sextet possibly be? Well, a sextet is a signal. A sextet is caused by 2 over here and 3 over here, for a total of 5 plus 1 is 6. But now, since we talked about complex splitting, we know there's no way that 2 protons on a carbon can ever be equivalent to 3 protons on a carbon. Just can't happen. There's no way that a CH3 can ever be equivalent to a CH2. So what we're looking at here, it's a sextet, but it has to be complex splitting that has simplified to simple splitting, because all of the coupling constants were fortuitously equal, right? There is no a sextet. There is no such thing really as a sextet. A sextet means a signal is split by 2 on this side and 3 on this side, or maybe 2 here, and 1 there, and nothing's equivalent to each other, all adding up to 5, but the coupling constants were all equal just fortuitously, right? So a sextet. A quintet is the very same thing. A quintet means the proton would have 4, a quintet means the proton would have 4 neighbors. So when we see a quintet, it could be 3 over here and 1 over here, right? But their coupling constants are all equal to each other, and that's why it looks like a quintet. We could have a real quintet with 2 over here and 2 over here, total of 4, and they could be equivalent to each other. That could give us a quintet, but we also could have a complex splitting multiplet that looks like a quintet. Okay. All right, so with that out of the way, now we can proceed to solve the structure. Let's try the most upfield signal first. It's a CH3. What does that mean? That means a methyl group. It doesn't have to, but that's the simplest explanation. It's split into a triplet. So what does that mean about who the neighbor is? The neighbor must be CH2, right? I'm calling him A, I'm calling him B, C, D, E, and F. So this guy here, I guess he's A. All right, and so now he's sitting next to a CH2. Is there a 2 hydrogen signal somewhere in the spectrum? There is, there are 2 of them, right? But this CH2 cannot arise from the signal near 3 ppm, because this CH2 would be split into a quartet, at least a quartet. So this CH2 here cannot be C. It has to be B. This has to be B, and it's a sextet because it's split by 3 on one side and 2 on the other side for a total of 5. Plus 1 is 6. It's a sextet. And so this guy, he's C. He's split into a triplet cleanly by the B. So we explained that, we explained that, we explained that. So that's where that sextet splitting is coming from. It's the B proton split by 3 on the left, 2 on the right, total of 5 neighbors, coupling constants all equal, n equals 5, 5 plus 1 is 6. Okay, so now when we look at the chemical shift of C, we see it's close to the, we see it's pretty close to, it's in the 2s, but we see a lot more downfield signals than that. Okay, so now let's go up, let's go downfield here. We have all of these 1 hydrogen signals. They are in the alkene region of the spectrum, right? Most of them are between 5 and 7. Let's take stock, 1, 2, 3, 4 carbons. We're looking for 2 more carbons. We're looking for another degree of unsaturation. It's an ester. These protons are in the alkene region of the spectrum. We have to be talking about a carbon-carbon multiple bond, a carbon-carbon double bond. Okay, and so 1, 2, 3, 4, 5, 6. We're looking at all of our carbon. We're looking at all of our oxygen. We're looking at all of our degrees of unsaturation. Now what we need to do is hook this thing up. Okay, so the C protons, their chemical shift is just too far upfield to be close to the oxygen. Being close to the oxygen lands the signal somewhere in the 3s. So I'm not going to hook this CH2 up to this oxygen. The chemical shift of the C is just wrong for that. The C's are, being close to this oxygen lands the signal in the 3s, not in the 2s. So I'm going to hook him up there, right? And this guy, I'm going to hook here. There's a hydrogen there, and a hydrogen there. So tell me, look at these hydrogens here. Which one is the F? Which one of these is the F proton? Well, it's probably this one, right? Closer to that oxygen. And he's split into a doublet of doublets by the E and the D. Right? Or this could be D, or it could be E. Right? We'd have to have a little bit more information to figure that out. But anyway, there's our structure, drawn in a prettier way. It would be this vinyl butyrate. Okay, so the F is split into a doublet of doublets by the E and the D. The E is split into a doublet of doublets by the F and whichever proton this is. So that's why we get this other doublet of doublets. And the same goes for this. Okay, so there's a problem that you're using complex splitting to determine the structure. All right, so at this point, we can draw a heavy double line there, and this will be the end of the material for quiz number 4. So quiz number 4 is going to be all about NMR, right? And what kinds of problems can you anticipate? Look at that study guide. It's going to be determining the number of signals. It's going to be sketching the spectrum from a structure. It's going to be determining the structure from a spectrum. What will the splitting pattern be, and so on and so forth. Okay, so now, but don't go away, because we need to especially since they're not going to have a lecture on Thursday, we need to forge ahead with new stuff. And now I want to talk about what today's lab is about, radicals. So let's dip into this. A radical is an odd electron species, right? Radicals don't have octets because octet means 8. 8 is an even number. So radicals are odd electron species. They have at least one unpaired electron. Okay, so from Gen Chem, we're familiar, say, on the periodic table, we would see a chlorine atom. Chlorine is group 7. That would be its Lewis structure. The chlorine atom is a radical, so we can also call it a chlorine radical. It has 7 valence electrons. It's an odd electron species. So that's a radical. When we talk about organic radicals, we can talk about the methyl radical, which has CH3 dot, and there's its Lewis structure, and that dot means the unpaired electron. It has a total of 7 valence electrons, an odd number, 7 electrons. Okay, most radicals are very reactive, very high energy, very unstable because they're dying to complete their octet. So most radicals live for about 1 microsecond at room temperature. There are some radicals that have that are perfectly stable. You can even buy them from Chemicals R Us, but most radicals, because they don't have an octet of electrons, most radicals live for about a microsecond because they don't have an octet. And they're just dying to complete their octet. So they're very reactive, very high energy species. Okay, so that's what a radical is. Let's talk about the different, let's talk about how radicals are formed. Radicals form by what is called homolytic bond breaking. So a homolysis or a homolytic bond breaking means that we have an atom A and it's bonded to atom B. What we do here is we either add heat or light. And what this does is the bond absorbs that energy input, either in the form of heat or light. It absorbs that energy input and that bond begins vibrating violently. It's absorbing a bunch of energy. It's vibrating, its amplitude gets bigger and bigger and bigger and bigger, and finally, snap, the bond breaks. But it breaks homolytically, meaning one atom takes away 1 electron from that bond and the other atom takes away the other electron from that bond. That is homolysis. The counter image of this is heterolysis, where one atom gets both electrons in the bond that used to unite them. That's not what we're talking about now when we're talking about radicals. And so we symbolize this by using the single-headed fishhook arrows, right? And these are kind of annoying. And so we would draw an arrow with a single head. See, that's supposed to be a fishhook arrow. And that means that 1 electron, right? That's why that arrow has 1 head. 1 electron went to the A, and the other electron, another fishhook arrow, another single head, went to the B. So this is how we conventionally represent the homolytic bond breaking. An orbital picture of this very same process would be the following. Let's say you have atom A, right? And here's his electron cloud. And then you have atom B, and here's his electron cloud. And these two got together to form a bonding sigma and an anti-bonding sigma molecular orbital. So there's A, and it is now stuck to B, right? So that's supposed to be its orbital. And this guy brought in one electron, B brought in one electron, and they went into this lower energy bonding sigma. But we also have, I think we talked about this briefly one of the first days of class, we also have an anti-bonding orbital up here. We have A and B in an anti-bonding orbital. And maybe we talked about how the anti-bonding orbital has different phasing and it has an extra node. So this is the anti-bonding. So this is the bonding orbital, right? This is the anti-bonding orbital. It's empty. Now, when we add heat or light, what is happening is that one of these electrons in the bonding orbital is being promoted up here to the anti-bonding orbital. And when we have as many bonding orbitals, bonding electrons, as we have anti-bonding electrons, the bond is not stable. If we have more anti-bonding electrons than we have bonding electrons, the bond is not stable. If we have the same number of bonding and anti-bonding electrons, the bond is not stable. So the addition of heat or light, the molecular orbital picture of this homolytic bond breaking, is that that one of these electrons is promoted up to that higher level. Look familiar? Yeah, like this is what's so similar to what's happening in NMR, right? You have these two energy levels and you have promotion from the lower energy orbital to the higher energy orbital. Okay, so that's how radicals form, by homolytic bond breaking. Heat or light. In the lab that you're talking about today, the system was heated to about 140 degrees. So that's pretty high up there, right? That would be Celsius, of course. Okay, so let's talk about the different types of radicals. Two kinds. Kind number one, this is called a pi accepting radicals. And a pi accepting radicals, we'll say why it's called that in a second. But the pi accepting radical atom is sp2 hybridized and planar. So a simple example of a pi accepting radical would be the the allyl radical, which looks like this, right? That's a pi accepting radical. And this is this carbon atom here. The carbon atom that hosts the radical dot is sp2 hybridized and it's planar. All right, so an orbital picture of this same guy would maybe look something like this. Here we have the pi bond between the two carbons. And here we have the hydrogen over here. There's a p orbital here, and there's an electron in there, right? And here we have the rest of the detail here, right? This is a p orbital. That's where the radical electron lives. This atom is sp2 hybridized and it's planar. All right, so that's what a pi accepting radical is going to look like. And we'll talk about why it's called pi accepting in more detail in a minute, but let me just tell you right now that pi accepting radicals are resonance stabilized. So we're going to get into resonance structures for radicals. And the two most common motifs that you see for pi accepting radicals would be the following. You have the radical dot. You have the radical dot sitting next to a multiple bond. It could be either a triple bond or a double bond, right? And the X and Y, they can be anything. They can be carbon atoms or nitrogen atoms or oxygen atoms or whatever. And the second most common motif that you see is that the radical dot is sitting next to an atom that has an unshared pair of electrons on it. This is how you recognize pi accepting radicals, is that the radical atom is sitting next to, but not part of, a multiple bond or sitting next to an atom that has an unshared pair of electrons. These are the situations where resonance becomes possible, and that's what makes them pi accepting. Okay, then we have the other kind of radical, and there's really no agreed upon term to what this is, so I'll just call it non-pi accepting. All right, and these are radicals that do not enjoy resonance stabilization. Just to repeat, you're looking for a pi accepting radical. What are you looking for? A dot next to a double bond, or a dot next to a triple bond, or a dot next to an atom that has an unshared pair of electrons. The non-pi accepting radicals are everything else. So for example, we could have the methyl radical, right? That's not pi accepting. Look at that radical dot. Is it sitting next to a multiple bond? No. Is it sitting next to an atom that has an unshared pair of electrons? No. That is a non-pi accepting radical. It does not take part in resonance. The non-pi accepting radical atom is sp3 hybridized, right? It's tetrahedral. So the methyl radical, what's a tetrahedron look like? It looks like a chicken foot. So the methyl radical would look something like this, sp3 hybridized, and the radical dot is in an sp3 hybrid orbital. But not only that, the non-pi accepting sp3 hybridized tetrahedral radicals, they are configurationally unstable. So they undergo a very rapid inversion. So the radical, so this tetrahedral with the feet, the chicken feet pointing down, goes through an inversion where it becomes a sp2 planar species, and then finishes up this inversion by being a radical where now it's legs up in the barnyard. The chicken died, it flopped over, and now its legs, its toes are pointing up in the air. So the non-pi accepting radicals undergo this inversion. It's kind of like an umbrella that's being blown by the wind and then being restored and then being blown up. And this is happening very, very rapidly. This guy is a transition state. It lives for about 10 to the minus 14 seconds. And then it either goes to the left or goes to the right. We can, with the activation energy for these processes, they have been measured. We can plug that delta E double dagger into that Eyring equation, and we come up with the rate constant for these processes, typically about 10 to the 9th per second at room temperature, right? Very, very, very fast. It's an up umbrella, then a down umbrella, up umbrella, then down umbrella, billions and billions of times per second at room temperature. Okay, so those are the two different types of radicals, the pi accepting radicals, and we know how to recognize them, and then everything else, which would be a non-pi accepting radical. Okay, so today, before get 10 more minutes, before time expires, let's talk about resonance structures of radicals. Okay, so here it's all the same rules for non-radical resonance, except, okay, so now some of the ways that writing resonance structures for radicals is different from writing resonance structures for stuff that isn't a radical. Okay, here we move single electrons using the fishhook arrow, right? The single-headed arrow. This is a pain, but I mean, this is how we show that we're moving single electrons rather than the two-headed arrow, which we use for regular resonance structures. Okay, so that's one way in which they're different. Another way in which the radicals, resonance structures for radicals are different is that destroying the octet of halogen, oxygen, and nitrogen is allowed, comma, but only to a septet. So remember that when radicals are forming, you're adding heat and you're adding light, right? You're adding the energy that is needed, that is required to make these highly electronegative atoms accept not having an octet. But you can't degrade the octet of these atoms any further than a septet. You can't degrade it to a sextet or a quintet or anything like that. So this is allowed here for radicals because remember, radicals form as a result of the input, sometimes of a whole lot of energy. You have the energy available for the octet to go away. Okay, how else is this different? How else is writing resonance structures for radicals different from for non-radicals? Is that you can move the radical dot, or you can ignore the radical dot. So in other words, you can write resonance structures that show that you're moving the radical electron, or you can write resonance structures where you're doing something else and you're just leaving the radical dot be. Okay, so those are the rules for writing resonance structures of radicals. Let's do an example. Oh, before we do this, let me just show you what the most common motifs will be. What will be the moves that you're doing? Okay, the common motif would be you have X, Y, and Z. Right, I'm just going through what would be the most common things that we do when we're writing resonance structures for radicals. So I'm going to move this dot. I'm going to move this dot here. See how I'm using the single-headed arrow? And so what this dot is trying to do, what X is trying to do, is complete its octet. It is going to do so by destroying the octet of something else. So it's going to unteam the pi bond here between X and Y, and this electron flows in here, and then the other electron flows to Z. So we've put in a double bond. X is happy now. X has an octet at the price of destroying the octet on the Z. See, now the radical dot looks like it's moved to Z. And this is what resonance is, right? This is delocalization of electron density. It looks like the dot, the electron moved from X to Z. All right, so that's a very common motif that we use. We could also accomplish this with a triple bond. So if we have the radical dot sitting next to a triple bond, it is going to unteam one of the two pi bonds, leaving the other pi bond be. So X is happy now. X has his octet at the cost, at the price of making Z a radical. Okay, so those are two common moves. The third common move that you see is when the radical dot is sitting next to an atom that has an unshared pair of electrons. Okay, here it's not as useful. The curved arrows, the fishhook arrows are not as useful. They're not really very useful anytime anyway, but here they're not as useful. We'll just get to what happens. What happens is that the electron, the X is looking to get an octet. It does so by robbing an electron from Y. So this is another common motif that we see when we write resonance structures for radicals. It looks like the dot and the single dot and the double dot changed places. What actually happened is that an electron on Y was delocalized. It moved, and that's what resonance is. It moved from Y to X. So that's another common motif that we see. So these are the three common moves that you're going to see where you're moving the radical dot. Okay, so before time expires, let's just get our feet wet here drawing some resonance structures for radicals. All right, so let's draw some resonance structures for this guy. Now, we can either ignore the dot or we can move the dot around. Let's write a resonance structure where we're ignoring the dot. So one of our most stereotypical move in all of resonance is the charge separation of the carbon-oxygen double bond. So there's a resonance structure. See, I didn't fool with the dot. I just let it be. Did I break any of the rules of resonance? No. This is neutral. I can create one new positive and one new negative. Did I destroy the octet of anything? No. So that's fine. Okay, so now let's write another resonance structure. Let's go back to this guy. Oh, this guy is of this type where you have the dot single bonded to an atom that has a double bond in it, right? X dot single bond, Y double bond, Z. So this radical fits into that scheme. There's the dot on the radical atom sitting next to, but not part of, a multiple bond. So here I could draw a resonance structure where I'm moving the dot around. Okay, and I could use the fish hooks. So now I have something that looks like this, right? This oxygen had 2 unshared pairs of electrons. It still has 2 unshared pairs of electrons. Sorry for this blob. But now I've created an oxygen radical. See how I destroyed the octet of that oxygen? But that's okay. I just can't knock it down any further than that. Okay, now I can draw another resonance structure that ignores the dot. Right, I'm just leaving that dot on the oxygen alone. And I'm writing a resonance structure that ignored the dot. Well, and that's okay too, right? Because I have one positive, one negative. Everything's fine there. And now this structure, that's back to this type, right? I see a double bond sitting next to a radical atom. So I could try to draw a resonance structure in which I'm going to restore that double bond. This oxygen atom has an unshared pair of electrons, has an unshared pair like that now. This is minus, and this is plus. Right, and so there's another resonance structure. Okay, so time has elapsed, and so next time we'll continue talking about writing resonance structures for radicals.